Hi, I'm Leah Brown, and I'm going to talk about my function failure identification and propagation analysis on the complex system of a biosafety level 4 laboratory. This analysis essentially adds on to the functional model produced in the last part and identifies the way that a critical error in one of the blocks will propagate through the system and assess whether the system could survive and still function with that block failing. Starting with the functional model, I decreased the size of my system a bit just because it was too complex to model in this way, and some aspects of it weren't applicable to this block diagram format. So I'm looking specifically at the redundant wastewater incinerators in drains of the biosafety laboratory. Essentially, this collects all of the runoff from the labs, which are rinsed down with bleach occasionally, and it boils them to a point where no microbes could possibly make it into the sewer system. So, looking at the first failure, which the propagation of which I assessed, was the liquid-liquid mix and the solid-liquid material mixing tank. Essentially, this is the drain. This is when stuff gets washed down. What this failure indicates is that only really solid liquids are going down. There's no bleach in this. It's because it got rinsed down with tap water or something. Essentially, this means that the first mix fails, but by the time we get to the second mix, the system picks back up where it left off, and the incineration goes on as normal, and the system carries on just fine. This means that the bleach is sort of an extra precaution, but not entirely necessary to the functionality of the system. Next, I'm assessing the failure of the branch distribution of the natural gas that powers the two incinerators. Essentially, if this valve that splits the natural gas supply into two were to clog or fail, then both incinerators fail, because they can't convert energy that doesn't exist, the liquid is not boiled, and dangerous pathogens could possibly be dumped into the sewer system. This means that this failure propagates in a critical way, and the system cannot do its job. The next failure I assessed was a regulation failure in only one of the incinerators. What happened here is that this redundant system did not perform its job, but it didn't propagate through the original system, and the complex system as a whole still functioned just fine. This illustrates the necessity of redundant systems when dealing with dangerous stuff. Next, I basically assessed what if the flame went out under one of the incinerators. I chose the other incinerator this time. The chemical energy is not converted into thermal energy. But, again, the second incinerator can pick up the slack, and the error does not propagate throughout the rest of the system. Again, illustrating the necessity of redundancy. Next, I looked at a failure in the sensing system, which contributes to the regulation of these incinerators. If one of the analog sensors failed, then essentially the regulation of one of the incinerators fails. This means that the conversion of energy fails, and then the mixing fails, and then that incinerator does not function as it should. However, the other incinerator is still functioning perfectly, and again, redundancy is key to this complex system performing its job. Next, looking at the failure of the condenser, which essentially cools down the incinerated fluid. If that fails, the fail propagates throughout the system, and what this basically means in this case is that steam is dumped into the sewers instead of liquid. This isn't ideal, but it doesn't actually affect the effectiveness of the system, as all microbes are still killed. Next, I looked at the failure of the signal processing unit. Yeah, that controlled the mixing in the first incinerator. What this essentially does is it means that one of the incinerators doesn't mix properly. But again, the second incinerator can pick up the slack, so the failure is not critical. Finally, I wanted to look at some of the failures in the feedback loop that operators actually see. An incinerator system like this would have a screen somewhere that they would look at to see how the system's functioning. And a failure in this screen could lead to alarm and an overall shutdown of the system in order to check its effectiveness. So these errors, while they might not affect the actual function of the incinerator, they can still affect the complex system as a whole. First, I looked at the failure of a conversion from the discrete control signal to a display that can be visually read. Essentially, this means that the engineer doesn't get any data. They shut down the entire system of the laboratory to look at the incinerators. This means data and work lost, but it doesn't violate the effectiveness of the entire system as a whole because no microbes escape. I also looked at just a failure of the mixture in one of the incinerators. And again, this just shows the importance of redundancy in this system, because even if one of these fails, the other doesn't. Finally, this is similar to the failure looked at in Figure 8. The display itself could fail. Everything else in the system could work perfectly fine. The display, however, could get waterlogged, the screen could crack, and something like that could cause an engineer to, again, shut down the entire laboratory to assess the function of the incinerators, just because they aren't getting proper feedback on how the system's running. So, looking at the system as a whole, the most important lesson learned from the function failure identification and propagation was that redundancy is what lets the system be as functional as it is, but also engineers need to be able to see that the redundancy is working the way it's supposed to, or they'll shut it down anyway and lose valuable time and data. Thank you.